If we look at streaming data from the last 5 Super Bowls, most people are watching the game 45 to 90 seconds after the action takes place on the field. This is true across all sports, not just the NFL. You could be watching a Game 7 home run 30 seconds after your cable watching neighbors have already erupted into cheers, and 45 seconds after your phone buzzed with the ESPN notification announcing the win. Or you're watching the Hungarian Grand Prix with a friend on a call, and they let out a lung-releasing gasp a whole minute before you witness Lance Stroll take out your favorite driver. I mean, if your friend was physically at the Formula 1 race, they could FaceTime the action across the globe with half a second delay? And you would watch it basically together. Then why is there such a large delay on streaming platforms? And why is there so much variation in how slow it actually is? Let's look at the actual technical reasons behind this latency, and why some massive changes happening to core parts of the internet might significantly improve this very soon. But first, if it's been a problem for years, why does anyone care now? Sports betting. The delay makes sports betting harder. Sports bettors like to make money, and they make more money by getting more bets. You have no doubt seen this, no longer just betting on the game's outcome, but also live in-game bets. Will the Chiefs score this drive? Will X pitcher strike out X batter this inning? But they want even more granular action. Will the offense get a first down this very next play? Will the leader pit this lap? Will this pitch be over or under 95 miles an hour? This is micro betting, the fastest growing segment in all of sports betting. Obviously, it would be less optimal to participate in these bets if you are watching over a minute behind the action. And the sports bettors, of course, can't hold the bet open for you to see it 90 seconds delayed, or they would be at risk for court-siding, or someone betting while witnessing the event sooner before it updates in the app, like physically being at the game courtside. So again, they are heavily incentivized to lower this delay of when you see the action so that you can bet more in these micro bets. And they have influence. Not only are they seemingly taking over all sports sponsors' real estate from every second of every commercial break to every inch of stadium signage, but they are now ultimately starting to bankroll some of the larger TV streaming deals themselves. Just one example is the NBA. They signed a deal to sell broadcast rights to NBC and Amazon Prime Video for a lot of money. Some argue too much money, as in they can never make that back amount of money. But right on cue, the sports betting operators signed massive exclusive deals with each, helping balance out some of the economics. It's fair to assume there is now significant pressure on streaming services that are signing these broadcast deals to decrease this latency. But even with all this pressure and money, it's still complicated technically, which is why I'm talking about it. Let's look at how these streams work today, by understanding what they are built on, and that is a recurring channel character TCP, or the Transmission Control Protocol. I'll go into the parts that matter here. TCP is the backbone of the reliable internet. TCP ensures that every packet sent over the internet arrives in order. If something gets lost, TCP resends it. But there are costs. One relevant to streaming is something called head-of-line blocking. If one packet gets delayed, everything behind it waits. Let's look at a typical implementation, though, of a sports broadcast stream to go a bit deeper. This stream uses an Apple-invented technology called HLS, or HTTP live streaming. Let's break these down, starting with understanding the basics of what this process is doing. Live video is received and broken down into chunks. It is broken down into 6 to 10 second chunks because chunks are efficiently transported over TCP. Now, the first encoder latency is simply the time it takes for these chunks to finish recording. A 10-second chunk means waiting the full 10 seconds before we can encode and compress it. MUX or multiplexing is a quick packaging step that combines video, audio, metadata, and more into a single container. And then we have a transmission step into a distribution encoding. This is usually off-site or in the cloud. This is more of a complicated encoding for creating the multiple different formats and bit rates and frame rates and resolutions for adaptive streaming. The timing here is the raw processing time. Now, the chunk gets sent to a content distribution network. This is where we actually get most of the efficiency of both TCP and this chunking of the live streaming we talked about earlier. This chunk is sent to hundreds of geographic distributed locations around the world to be cached, then requested by individual players or your TV. The CDN here is essentially dramatically decreasing the cost and load on the whole network while delivering only to each individual device the short distance or last mile. Now, your device won't just play it once it comes in though, it needs to build up a buffer of multiple of these chunks. This keeps the stream playing during network interruptions and allows it to adjust quality adaptively. But this also means that depending on how the player decides what a live chunk is, you not only get the natural massive buffer delay, but a variation in the delay. Overall, that puts HLS at least here if we wanted to start mapping out these delays on a chart. HLS is simple, reliable, and significantly cost-effective. Those large chunks are more efficiently compressed and delivered to devices. Also, aside from the latency problem, it's a good experience. It's why you can easily watch live sports in bad networking situations, like on your phone, going in and out of service, which is less true for the other side of the chart. Things like using Zoom or FaceTime or other video conferencing tools with near real-time latency. These tools mostly use a technology called WebRTC, which is based on TCP's hyperactive cousin, UDP. While TCP does a ton of work to make sure data is reliable and in the proper order, UDP is just a fire hose of data. WebRTC runs on UDP. No guarantees, no acknowledgement, just send the data as fast as possible. You lost a packet? Move on. For video calls, this works. Would you rather have a glitch for a frame or two on a Zoom call, or freeze for 5 seconds while TCP retransmits? This is where you get the blockiness and weird audio glitches and everything else that comes with calls on a bad network. But it's real time. WebRTC is at its core a peer-to-peer protocol. In most use cases, your video goes directly to the other person. It does not need to use any intermediary server infrastructure, and achieves latencies of just a few hundred milliseconds. But WebRTC has problems at scale. Peer-to-peer doesn't work for millions of viewers. The math of peer-to-peer would make it physically impossible. Like, not just physically impossible for the current internet, but like math and physics? In a mesh network, the number of connections grows quadratically with every new participant. It's a n-squared problem. Even with routing optimizations and the fact that you can have WebRTC from a source media server, as in the peer being a central server fanning out to clients called a selective forwarding unit, it would still require building what is essentially private stateful real-time CDNs, a complex and expensive undertaking. Ultimately, it struggles to scale to massive audiences because it still needs to maintain computationally intensive connections to each device. Plus, it's not set up to handle everything else expected for a broadcast stream, such as DRM and closed captioning and ad insertion, and really important features such as pausing and rewinding and on-demand playback. All these problems add up to make video streaming with WebRTC monstrously expensive. This does not mean WebRTC is not useful though. It tends to be the most commonly used tool for real-time stats on the actual betting platforms themselves, like how they update the markets and odds in real time, but not for transmitting the expensive, high bandwidth video content. But we can still put WebRTC in the chart. This leaves a wide gap of opportunity. What if we could give up some of the reliability and simplicity of HCL for less delay? Insert low-latency HLS, or LLHLS. There's a lot that goes into these new protocols, but the most important part is shrinking chunks from 6 to 10 seconds down significantly, and some new technology that allows it to send partial segments as they're created. The encoder can start delivering chunks before the full segment is even encoded, reducing the 8-second encoding latency to 1 to 2 seconds since you're not waiting for these complete segments. But this is complicated and requires a mountain of new tech, protocols, and patchy workarounds to get it all working together. It's essentially squeezing every drop from a system never designed for this. Smaller chunks means less efficiency and worse economics. For example, most CDNs charge for data and requests. A traditional HLS streams 6-second segments. That might be one individual request. The same duration LLHLS could be 10 to 24 chunk requests, and those chunks and requests are way less efficiently cached, which means even more expense. Some CDNs charge 10 to 50 times more for low latency HLS delivery due to the increased request overhead. But like I mentioned earlier, there's a lot of money involved. So if we also add some other expensive operations like hardware encoding with expensive FPGA encoders, low latency HLS can have a latency of 2 to 5 seconds, glass to glass, which puts it about here on the chart. But the user experience here can suffer. A traditional HLS buffer can tolerate a full 1 to 2 second network hiccup, while low latency HLS buffer can only tolerate a few hundred milliseconds max. And for most viewers, especially those that are not betting, freezing and buffering are worse than latency. That being said, we do see some of these low latency and ultra low latency systems slowly being rolled out. Sometimes it's hidden behind a user setting like on YouTube TV, but it has seen some real results. For the first time during the 2025 Super Bowl, a single streaming service was faster than cable. Tubi over Fire TV of all combos, but this was only for certain customers in ideal conditions. So this is where we are right now. Do the tried and true HLS, it's cheap, it's simple, but it's delayed. But high quality and a good experience outside of interactivity and things like sports betting. Or pay a ton of money to get fast. In many cases, double-digit multiples more money. And it can still be a worse experience for customers. Now, in fairness, the reality is more complicated. Many large systems do a proprietary mix of multiple protocols we discussed and choose optimizations and fallbacks that suit their platform. But even with the money and ability to handle complexity by, let's say, a company like Netflix, the backbones of the internet struggle to keep up on the inefficiencies of large live streams on some of these patchworks of protocols. In 2024, Netflix live streamed a fight between Mike Tyson and Jake Paul. You've probably heard of it. It famously didn't go so well. There were some technical issues for many of the 65 million who chose to watch it live. The CTO of Netflix mentioned in an interview that there were some connection challenges between their CDNs and ISPs, and that the stream was stressing the limits of the internet itself. And I believe him. Yeah, they had some issues of their own, but last mile internet service providers were also falling over during the stream. It was not just Netflix, but ISPs as well. It's just a lot of data and a lot of requests, especially when trying to bring down the latency, which Netflix was doing. But there might be a solution here on the horizon. The industry is coming together around a new protocol called QUIC. QUIC is not just for streaming, it's built into the newest version of HTTP. HTTP, or the protocol that gives us the web, was traditionally run on TCP. It's reliable and stable. But with QUIC, it runs on UDP by building much of the reliability of TCP into the application layer on top of the firehose of data that is UDP. And importantly, fewer round trips and fewer blocking operations than TCP. No more head-of-line blocking, as we discussed earlier. Data keeps streaming. If a packet is missed, it's still retransmitted in the background. The best of both worlds. QUIC is here and already changing how the web operates today. Hell, you're probably watching this current YouTube video using QUIC as we speak, as it was invented and is heavily utilized by Google and YouTube. Using QUIC for streaming is an obvious next step. So, enter Media over QUIC, or MOQ. Although it's still in development, going through the Internet Engineering Task Force, it has some big names backing it, claiming to have the speed of WebRTC and the scalability of HLS. A big claim, but MOQ aims to be a foundational internet technology to replace many of the tech that we have talked about during this video. Instead of your device requesting each chunk one by one, MOQ flips this around. The source publishes and broadcasts chunks as they are created, and your device subscribes to the stream. Chunks flow continuously without all those individual expensive requests we talked about earlier. This means way less overhead, way fewer round trips, and because it's built on QUIC, if one chunk has an issue, it doesn't block the others behind it. Plus, MOQ can dynamically adjust quality midstream without breaking the connection, something most UDP-based protocols never could do. But MOQ isn't fully ready for prime time yet. First, the spec itself is still being finalized by the IETF. We're talking about trying to replace decades of established internet infrastructure. That doesn't happen overnight. And, well, not all browsers fully support it yet, and CDN infrastructure will also need to update. But because MLQ uses QUIC in these UDP streams, it's far more efficiently streamed over CDNs, and the biggest players are actively involved and already supporting it. So while MLQ is promising, it's not here yet, but it's coming, especially considering the money and technical players involved. As you're watching the big game, or the Olympics coming up right after that, or any other live event, hopefully you now understand a bit more of the work to get that to your screen, and some of the changes that might be coming soon. Thanks for watching. If you like learning about how the internet works, check out my video on why downloads look like waves. Or if you want to hear a fun story, check out my video on the history of the Japanese internet and how it started legally. Or subscribe, and I'll see you in the next one.